Before we get started, please remember that this video is for informational purposes only. Working with plumbing involves water pressure and the risk of property damage. If you are not confident in your ability to perform these steps safely, or if you're dealing with a major leak, please turn off the water to the fixture or the building and call a licensed professional plumber. Your safety and your property come first. A single, constantly running commercial toilet can waste over 70,000 gallons of water in a year. 70,000 gallons. Now multiply that by the number of restrooms in your building. That's not a drip. That's a river of your profits flowing directly into the city sewer system. It's the kind of hidden expense that eats away at your bottom line month after month. And most people don't even notice until they get that one water bill that makes their eyes water. Imagine this. It's peak business hours. The phone is ringing, customers are waiting, your team is stretched thin. And then your front desk person gives you that look. The look that says, "We have a problem." A customer has just told them the toilet in the main restroom has been running for the last half hour. You walk in and you hear it. Not the sound of a flush, but the relentless hissing sound of a waterfall. It's the sound of a system failing, the sound of a bad customer experience in the making, and the sound of your utility budget being set on fire. That sound is why you're here. And I'm going to give you the ultimate guide to silencing it for good. We are going to break down the top 5 reasons your commercial toilet won't stop flushing. We're not just going to talk theory. I'm going to give you a step-by-step diagnostic playbook. You'll learn how to identify the exact cause of the problem, from the incredibly simple to the surprisingly complex, so you can stop guessing and start fixing. For most of these issues, you'll be able to fix it yourself in under 20 minutes with basic tools, saving you a $200 service call. By the end of this presentation, you will understand that intimidating chrome fixture better than 99% of business owners, and you'll have the confidence to tackle this problem head-on. Now let's be honest. That big chrome device on top of the toilet, the flushometer, it looks intimidating. It's not like the toilet in your house with the friendly flapper and the float ball. This thing looks like it belongs on a submarine. But there's a reason for that. Commercial toilets are built for war. They're designed to handle hundreds of flushes a day, withstand abuse, and reset in seconds for the next user. They're powerful, they're efficient, and they're actually brilliantly simple once you understand what's going on inside. That complex-looking chrome body is just a housing for a few key parts that work together in a very logical way. And once you know those parts, you can diagnose any problem. So we're going to count down the top 5 most common failures that cause a commercial toilet to run, starting with number 5. Reason number 5. A worn-out or damaged diaphragm kit. This is, without a doubt, one of the biggest culprits. The diaphragm is the heart and soul of the flushometer. It's the engine that drives the entire flush. Think of it like a valve and a timer all in one. It's a flexible rubber disc, often with a few other small plastic components, that sits inside the main body of the flushometer. When you push the handle, you're essentially relieving a tiny bit of water pressure on top of this diaphragm. This pressure difference causes the diaphragm to lift up, unleashing the full force of the water supply line down into the toilet bowl. That's your powerful flush. But here's the magic. As the water rushes out, a tiny bypass hole in the diaphragm slowly allows the upper chamber to refill with water. Once the pressure on top equalizes with the pressure below, the diaphragm is forced back down onto its seat, shutting off the flow of water completely. It's a brilliant, self-contained hydraulic system. So what goes wrong? Well, that rubber diaphragm is a moving part, and it lives in a harsh, watery environment. Over thousands of flushes, it can become stiff, warped, or develop tiny tears. More commonly, sediment, rust, or mineral deposits from the water, what plumbers call scale, can get lodged in that tiny bypass hole. If that hole gets clogged, the upper chamber can't refill properly. If it can't refill, the pressure never builds back up to force the diaphragm down. And if the diaphragm doesn't go down, the water never stops running. You get a constant, steady flow of water into the bowl that will not quit. Alternatively, if debris gets stuck under the rim of the diaphragm itself, it can't create a perfect seal when it closes. This results in a slow, constant, and very wasteful leak into the bowl, long after the flush should have ended. So how do you know if the diaphragm is your problem? The symptoms are pretty clear. First, the toilet just won't stop running at all. It's not a ghost flush, it's a permanent flush. Second, you might get a very weak flush followed by a slow refill that never seems to shut off. The user flushes, the water swirls weakly, and then it just keeps trickling in. The fix is surprisingly simple, and it's a great first step in any repair. First, and this is the most important step for any plumbing work, you have to shut off the water. On a commercial flushometer, you don't have to run to the basement. There's a built-in shutoff valve called a stop valve, right on the pipe leading into the flushometer. It will have a flathead screw slot on it, usually covered by a chrome cap. You'll need to pry that cap off gently with a flathead screwdriver. Then use that same screwdriver to turn the screw inside clockwise until it stops. This shuts off all water to that specific toilet. Next, you need to relieve the water pressure. Just push the flush handle one time. You'll hear a little pfft, and that's it. Now it's safe to open. The top of the flushometer is a big chrome cap. You'll need a large wrench or a pair of smooth-jawed pliers to turn it counterclockwise. A quick tip: wrap the cap in a rag before you put the wrench on it to avoid scratching that beautiful chrome finish. Once you loosen it, you can unscrew it by hand. Lift it off, and right there underneath you'll see the diaphragm assembly. Just lift it straight out. Take a close look at it. Is the rubber cracked or warped? Is there gunk or a piece of debris stuck in that tiny little hole? Even if it looks fine, these kits are so inexpensive, usually $10 to $15, that it's almost always worth replacing it if you've gone to the trouble of opening the valve. Take the old one with you to the hardware store or a plumbing supply house to make sure you get the exact match. They come in different gallons per flush ratings, so matching the old one is critical. Drop the new one in, make sure it's seated correctly, screw the top cap back on hand tight, give it a final snug with the wrench, turn the water back on, and you've likely just solved your problem. Now what if you do all that and the problem is still there? Or maybe the symptoms are a little different? That brings us to reason number 4. A faulty or sticking handle assembly. It sounds too simple to be a real problem, but you would be shocked how often this is the issue. Everyone thinks the handle is just a simple button, but it's a precision mechanism. When you push the handle, a small plunger inside moves forward and activates a relief valve, which is what starts the whole chain reaction with the diaphragm. The handle is spring-loaded, so it should immediately return to its starting position, allowing the relief valve to reseat. But what happens when it doesn't? If the handle sticks even a tiny bit, it's holding that relief valve open. And if the relief valve is open, the diaphragm will never be able to close. The result? A constantly running toilet. This happens for a few reasons. The internal spring can weaken or break over time. The seal around the handle's plunger, often a little rubber O-ring, can wear out, causing it to bind. Or, just like with the diaphragm, mineral deposits and gunk can build up inside the handle mechanism, causing it to become sticky and sluggish. The telltale sign of a handle problem is that you can often stop the leak by manually fiddling with the handle. If you push the handle and the toilet starts running, but then stops if you jiggle the handle or pull it back out manually, you've found your culprit. It's the commercial version of having to jiggle the handle on an old residential toilet. The fix here is also straightforward. After shutting off the water and relieving the pressure, you'll see a retaining nut that holds the handle assembly to the body of the flushometer. You can usually unscrew this with a wrench. Once it's off, the entire handle assembly will pull straight out. You can buy a replacement kit for just the handle, and it's often the easiest solution. But sometimes you can repair the existing one. Take it out and inspect it. Is the spring broken? Is it full of crusty buildup? You can often clean it thoroughly with a small brush and some vinegar to dissolve the mineral deposits. You can also buy replacement O-rings and gaskets for the handle specifically. A little bit of plumber's silicone grease on the seal, when you reassemble it will make it operate smoothly and last much longer. Reinstall it, tighten the retaining nut, turn the water back on and test it. A crisp, clean flush with a handle that snaps right back into place is what you're looking for. It's a simple fix, but it's one that gets overlooked all the time because people are so focused on the big, main valve body, they forget about the trigger that starts it all. But what happens when the trigger fires perfectly, but the cannon just keeps on firing? The handle snaps back, you hear that satisfying click, but the water rages on. A relentless waterfall in a porcelain bowl. This, my friends, brings us to the number 2 reason your commercial toilet is stuck in a flushing frenzy. And it's the absolute heart of the entire operation, the diaphragm. Inside that chrome-plated flushometer body, that tough metal fortress, lives a simple, flexible rubber disc. That's the diaphragm. Think of it as the bouncer at the world's most exclusive nightclub. Its job is to stand at the door, holding back an incredible amount of water pressure. When you push the handle, you're basically telling the bouncer to step aside for a few seconds, let a specific number of patrons, in this case gallons of water, into the club, and then slam the door shut. The diaphragm is what separates the high-pressure water in your supply line from the low-pressure chamber inside the valve. The magic of the flush is all about manipulating the pressure on either side of this rubber disc. When it works, it's a beautiful, elegant piece of fluid dynamics. But when it fails spectacularly. I once got a call from the facilities manager of a major sports arena. He was panicked. He said their water bill for the last month looked like the budget for a small nation. After a bit of digging, they found the culprit. It wasn't a huge, catastrophic pipe break. It was a single urinal in a little-used locker room. The diaphragm inside its flushometer had failed. It had been running full blast 24 hours a day, 7 days a week for over a month. We're talking about thousands upon thousands of gallons of water, literally washed down the drain, all because a single $10 rubber component gave up the ghost. That's the power and the peril of the diaphragm. So how does this bouncer get taken down? There are 3 main assassins. The first is simply old age. Like any rubber product, a diaphragm has a lifespan. Over years of flexing, sealing, and being bombarded by water pressure, it gets brittle, cracks. It can develop a warp, losing its perfectly flat shape, which means it can no longer create that perfect seal against the valve seat. You might see tiny hairline fractures, or the outer edge might look chewed up and uneven. When that happens, water starts to leak past the seal, the pressure balance is thrown off, and the valve never gets the signal to fully close. The second assassin is your water. Or more specifically, what's in your water. If you live in an area with hard water, calcium and magnesium deposits, what we call scale, can build up on the diaphragm and the valve seat. This creates a rough, gritty surface where a smooth, perfect seal is needed. It's like trying to close a Ziploc bag with a bunch of sand in the track. It's just not going to seal. On the other end of the spectrum, the chemicals used to treat municipal water, especially chloramine, can be incredibly harsh on rubber components. Over time, chloramine will literally eat away at the diaphragm, making it soft, gummy, or causing it to swell up. A swollen diaphragm won't fit correctly in its chamber, and a gummy one won't have the structural integrity to hold back the pressure. But the third and most common assassin, the one that can take out a brand new diaphragm in a matter of minutes, is debris. A single grain of sand, a tiny flake of rust from an old pipe, a piece of solder from a sloppy installation. If any of that gets inside the valve, it can be game over. This debris can get lodged under the diaphragm, preventing it from seating and sealing properly. It's the classic rock in the door problem. The door can't close because something is physically holding it open. This brings me to the number 3 reason your toilet won't stop flushing, which is so closely related to the diaphragm that they're practically partners in crime. It's not a part you can easily see or even buy in a store. It's a feature, not a component. I'm talking about the bypass orifice, or as plumbers often call it, the weep hole. To understand this, you have to understand how the diaphragm knows when to close. Remember how I said it's all about pressure? On top of the diaphragm, there's a small chamber that's also filled with water. When you flush, the handle mechanism releases the water from this top chamber. With high pressure below it and no pressure above it, the diaphragm is forced upwards, opening the floodgates to the bowl. The flush begins. But for the flush to stop, that top chamber needs to refill with water to equalize the pressure and push the diaphragm back down onto its seat. And how does it refill? Through an absolutely minuscule, pin-sized hole drilled through the diaphragm itself. This is the bypass orifice. It's an engineering marvel. This tiny hole is precisely calibrated to allow water to slowly seep back into the top chamber, taking just the right amount of time, usually a few seconds, to build up enough pressure to slam the diaphragm shut and end the flush. It's what determines the timing of the entire cycle. It ensures you get a full, powerful flush but not a drop more. Now, imagine what happens when that tiny critical passageway gets clogged. A single grain of sand, a microscopic piece of sediment, is all it takes. If the weep hole is blocked, the top chamber can never refill with water. The pressure never equalizes. And that bouncer? He's stuck holding the door open forever. The diaphragm stays lifted, and the water runs and runs and runs because the valve never gets the signal to shut down. This is one of the most frustrating problems to diagnose because you can pull out a diaphragm that looks perfectly fine. It's not torn, it's not warped, it's not brittle. You might even replace it with a brand new one, put the toilet back together, turn on the water, and the problem is still there. The water continues to run. It's maddening. You're left scratching your head, thinking the brand new part must be faulty. But the problem isn't the diaphragm itself, it's the blocked bypass. The signal is being sent, but the message is never received. So how do you spot this? A key symptom of a clogged bypass is a toilet that flushes once, and then just continues to run at full blast. It doesn't try to shut off, it doesn't sputter, it just flows. It's as if the off switch has been completely disconnected from the system. If you take the diaphragm out and hold it up to a light, you might be able to see the tiny hole. But often the debris is packed in there so tightly you can't see a thing. It looks like it was manufactured without a hole at all. This is incredibly common in new construction, or after a major plumbing repair in a building. When you cut and solder pipes, or when the city works on a water main down the street, it stirs up decades of sediment and debris inside the water lines. This junk then flows downstream to the first fixture it finds, and that tiny precision-engineered weep hole acts like a perfect filter, catching the very first piece of grit that comes its way. One plumber I know calls it new construction syndrome. He'll walk onto a site with 50 brand new toilets, and 10 of them will be running continuously right out of the box, all because of debris in the lines clogging that tiny, all-important orifice. So the million-dollar question is, how do you fix it? You have this microscopic hole plugged with who knows what. Your instinct might be to grab something sharp, a paper clip, a safety pin, the tip of a knife, and just poke it through. And let me tell you right now, that is the single worst thing you can possibly do. Because the size of that hole isn't an accident. It's been engineered down to the thousandth of an inch. If you jam a paperclip in there and enlarge that hole by even a fraction of a millimeter, you've just destroyed the timing of the entire valve. The chamber will now fill up too quickly, the diaphragm will slam shut too soon, and you'll be left with a weak, partial flush that can't even clear the bowl. You've traded one problem for a completely different and arguably worse one. You've turned a running toilet into a toilet that doesn't flush at all. And fixing that requires a tool so precise you might not even think of it as a tool, but using the wrong one could mean you're buying a whole new flush valve. That tool is a single bristle from a wire brush. Or, if you're a purist, the tiny specialized brass pick that comes inside a genuine Sloan rebuild kit. It's a tool so small, so insignificant, you could drop it on the floor and never find it again. But the job it does is based on a principle of physics so fundamental. It's the reason a 50-pound metal valve can be controlled by the gentle push of a finger. And understanding that principle is the key to fixing our third most common reason for a phantom flushing toilet: a clogged bypass orifice. Now, I know we just created a toilet that won't flush at all, and the video is about a toilet that won't stop. Stick with me, because these two problems are two sides of the exact same coin, and that coin is spinning on the head of a pin inside your flushometer. To understand this, you have to understand the elegant, almost beautiful engineering at work. Inside that chrome dome, you have two separate water chambers, an upper chamber and a lower chamber, divided by that flexible rubber diaphragm we talked about earlier. Think of the diaphragm as a massive, heavy door. The lower chamber is the public area, connected to the toilet bowl. The upper chamber is the control room. When the toilet is just sitting there waiting, both chambers are filled with water and are at the exact same pressure, let's say 60 psi. Because the surface area on the top of the diaphragm is much larger than the area on the bottom, that equal pressure exerts more total force pushing down than it does pushing up. Simple physics. This massive downward force is what seals the diaphragm shut, keeping water from flowing into the toilet. It's a perfect, powerful seal. When you push the handle, you're not physically lifting that heavy diaphragm. You're not a superhero. All you're doing is tilting a small plunger, which briefly opens a release valve, letting the water out of that upper chamber. With the pressure suddenly gone from the top, the 60 psi of pressure in the bottom chamber now has nothing to fight against. It easily shoves that diaphragm door wide open and whoosh, a torrent of water rushes into the bowl. That's your flush. But here's the magic. How does the flush stop? How does that top chamber repressurize itself to slam the door shut again? The answer is a hole. A hole so tiny you could barely see it. It's called the bypass orifice. It's a minuscule channel drilled through the center of the diaphragm that allows a tiny, precisely metered trickle of water from the lower chamber to flow back up into the top chamber. As the top chamber slowly refills through this tiny hole, pressure builds back up on top of the diaphragm until slam, it has enough force to push the diaphragm back down, sealing the valve and ending the flush. The entire flush cycle, from the whoosh to the slam, is dictated by the size of that tiny hole. Too small and the flush is too long. Too big and the flush is too short. It has to be perfect. And our problem, the reason your brand new diaphragm didn't fix your running toilet, is that this perfectly engineered hole is now completely clogged. A single grain of sand from the city water main, a tiny flake of rust from an old pipe, a piece of sediment, that's all it takes. It gets wedged in that orifice, blocking it completely. So let's trace the failure. You push the handle. The top chamber's water is released. The bottom pressure shoves the diaphragm up. Whoosh! The flush begins. But now, because the bypass orifice is clogged, there is no way for water to trickle back into the top chamber. There's no way to rebuild the pressure needed to close the valve. So the diaphragm just stays open, and the water runs, and runs, and runs, forever. You have an infinite flush. This is where people make a catastrophic mistake. They correctly diagnose the problem, a clogged hole, and they grab the first tool they can find, a paper clip, a safety pin, the tip of a pocket knife. They jam it into that tiny orifice to clear the debris, and it works. The debris is gone. They put the valve back together, turn on the water, and now the toilet won't flush at all. What happened? They've just fallen victim to the difference between brass and steel. That little orifice is drilled into soft brass. A steel paperclip is like a surgeon's scalpel against it. By ramming it in there, they didn't just clear the debris. They scraped the inside of the orifice, peeling off a tiny curl of brass. A burr, that's now partially blocking the hole. Or worse, they've gouged the sides, changing its diameter. Remember, the size of that hole is a product of careful engineering. By damaging it, you fundamentally altered the physics of the valve. Now when you flush, that trickle of water that's supposed to refill the top chamber is either too restricted by the burr, or it's flowing too fast because you've widened the hole. The delicate balance is destroyed. Often the result is a valve that can't build enough pressure to close, or one that closes so fast you don't even get a full flush. You tried to fix a running toilet and created a non-flushing toilet. This is why the right tool is not just a suggestion. It's a requirement. That single bristle from a wire brush is strong enough to dislodge a piece of sand, but it's flexible and soft enough that it won't damage the brass. The official Sloan tool is even better, as it's made of a softer metal. The goal is to clean, not to carve. You gently, carefully work the tool into the orifice, clearing the obstruction without altering the hole's dimensions. You're performing microsurgery on your toilet. When you do it right, the result is beautiful. You reassemble the valve, turn the water on, and the toilet that was running non-stop is now silent. You push the handle, you get a perfect, powerful 3.5-second flush, and then silence. You have restored the elegant balance of pressure that the engineers intended. You fixed the problem for $0, using a tool you probably had lying in a dusty corner of your garage. And this brings us full circle. A completely clogged bypass orifice causes a never-ending flush. But what happens if it's only partially clogged? Or more importantly, what happens if a previous handyman took a drill bit to it, thinking a bigger hole meant a better flush? This is the other side of that coin. If the orifice is damaged and made too large, water flows back into the top chamber too quickly. The pressure equalizes almost instantly. You'll push the handle, the diaphragm will pop up for a split second, and slam, it shuts again before a full flush can even happen. This is called a short flush, and it's a classic symptom of an orifice that's been improperly cleaned or intentionally widened. So you see, this one tiny pinprick of a hole is the brain of the entire operation. If it's clogged, the valve never closes. If it's damaged and too wide, it closes too soon. It has to be perfect. And checking it and cleaning it correctly is one of the most critical steps in diagnosing a commercial toilet. But what if you've done all of that? You've replaced the diaphragm. You've meticulously cleaned the bypass orifice with the proper tool. You've reassembled everything perfectly. You push the handle and the toilet still runs for 20 seconds, 30 seconds, a minute, before finally shutting off. It's not infinite, but it's way too long, wasting gallons with every flush. The parts are good. The theory is sound. So what else could be wrong? The answer is our fourth reason, and it's a problem that has nothing to do with a clog or a broken part. It has to do with the lifeblood of the system itself, the water. And more specifically, how much of it is getting to the valve in the first place. You could have the most perfect flushometer in the world, but if it's being starved of water, it will misbehave in ways that will make you want to tear your hair out. It's a deceptively simple concept that's at the heart of so many maintenance nightmares. Think of the flushometer valve like a world-class athlete. It's designed for explosive, powerful performance. But if you only feed that athlete a few hundred calories a day, they're going to collapse. They won't be able to perform, no matter how perfectly trained they are. Your flushometer is that athlete, and the water supply is its fuel. When it's starved, it doesn't just get weak. It completely forgets how to function. This brings us to the second major reason your commercial toilet won't stop flushing. Insufficient water pressure and volume. This is the silent saboteur. It's the invisible force that can make a brand new, perfectly installed valve act like it's 100 years old and ready for the scrap heap. And because you can't see it, it's often the last thing people check. after they've already spent hours and hundreds of dollars replacing parts that were never broken in the first place. So how does this actually work? Why does a lack of water pressure or volume cause a toilet to run continuously? It all comes back to that delicate balancing act happening inside the valve body. Remember, for the valve to shut off, water needs to flow through that tiny bypass hole in the diaphragm, fill the upper chamber, and create a downward force that's greater than the upward force of the incoming water. This slams the diaphragm down onto the valve seat and stops the flow. But what happens when the incoming pressure is too low? The system breaks down in two critical ways. First, the flush itself is weak and lazy. You push the handle and instead of that satisfying whoosh, you get a weak swirling flush that barely clears the bowl. That's your first clue. But the real problem is what happens next. Because the incoming pressure from the supply line is so feeble, it doesn't have enough oomph to properly push the diaphragm back up and reseat it after the flush. The water in the upper chamber drains out, but the system never gets that critical reset pressure from below. The diaphragm just kind of hovers. It floats in a state of purgatory, never fully closing, allowing water to constantly leak down into the bowl. Low volume is just as bad, if not worse. You might have decent static pressure, meaning if you put a gauge on the pipe when nothing is running, it reads a healthy number. But the moment you open the valve, that pressure plummets. This is like trying to drink a thick milkshake through a tiny coffee stirrer. There's plenty of milkshake in the cup, but you can't get it out fast enough. In a plumbing system, this means there isn't enough water moving through the pipes to properly refill that upper chamber in the valve. The flush starts, the chamber empties, but it can't refill fast enough to create the downward sealing pressure. So the valve just stays open, waiting for a volume of water that will never arrive. Let me tell you a story that perfectly illustrates this. There was a brand new 10-story corporate office building in Chicago. Gleaming glass, state-of-the-art everything. But they had a plague on the top 3 floors. The men's and women's restrooms were a constant symphony of running toilets. The building's facility manager was at his wit's end. His team had replaced the diaphragm kits in every single flushometer. When that didn't work, they replaced the entire flushometer units. Still, the ghost flushing continued. They called the manufacturer Sloan, convinced they had received a bad batch of valves. They were losing their minds, and the tenant, a high-powered law firm, was losing its patience. Finally, they called in an old-school master plumber, a guy named Frank who had seen everything. Frank walks into this pristine, marble-tiled bathroom on the 10th floor, listens to a toilet hissing away, and doesn't even touch it. He ignores the shiny chrome valve completely. Instead, he walks over to the janitor's closet on the same floor and hooks a pressure gauge up to the utility sink. He turns on the water and just watches the needle. Then he has one of the maintenance guys go and flush 2 toilets at the same time. The needle on his gauge dropped like a stone. He turned to the frantic facility manager and said, "Your problem isn't in the bathrooms. It's in the basement." It turned out, the booster pump system that was supposed to ensure adequate water pressure to the upper floors of the high-rise was miscalibrated. It was providing just enough pressure to meet the minimum code when nothing was running, but the moment you had simultaneous use, a couple of flushes, someone washing their hands, the system couldn't keep up. The volume and dynamic pressure on the top floors were abysmal. The flushometers weren't failing. They were being failed by the building itself. They were being starved, and they were letting everybody know about it. The fix had nothing to do with a wrench on a toilet. It involved an engineer reprogramming the building's water pump controller. So how do you diagnose this without calling in an expensive master plumber? You start with the simplest and most overlooked component on the entire fixture: the control stop. That's the screw or knob on the pipe just before the flushometer. Its job is to both shut off the water for service and to regulate the flow. This is not just an on-off switch. Many well-meaning but inexperienced maintenance guys will crank this stop down, thinking they're conserving water or making the flush quieter. What they're actually doing is strangling the valve. They are artificially creating a low-volume situation. Here's the right way to set it. First, shut off the water to the bathroom. Then, open that control stop counterclockwise all the way until it stops. Then turn it back clockwise just a half turn. That's it. That's the factory recommended setting for most flushometers. It ensures the valve is getting the maximum available volume from the pipe. If adjusting the control stop solves your problem, you just saved yourself a massive headache. But if the problem persists, you need to think like Frank the plumber and look upstream. Are the sinks on that same floor showing weak flow? Does the running toilet problem get worse during peak hours, like lunchtime in an office building? That's a huge red flag for a systemic volume issue. The building's plumbing is like a highway system. If there's a 5-car pileup on the main interstate, the traffic on every side street is going to slow to a crawl. If you want to get serious, you can buy a simple water pressure gauge for less than $20 at any hardware store. Find a hose bib or a utility sink as close to the problem toilet as you can. Screw on the gauge. First, measure the static pressure. That's the pressure with all the water off. Let's say it reads 65 psi. Looks good, right? Now, keep the gauge on and have someone flush the problem toilet, and maybe even another one nearby. Watch the needle. If it drops from 65 down to 20 psi, you don't have a toilet problem, you have a water supply problem. That massive drop is called pressure drop, and it's the smoking gun for inadequate volume. What causes this system-wide starvation? It could be a failing booster pump like in our story. It could be a malfunctioning pressure-reducing valve, or PRV. That's choking the supply to the whole building. But often, in older buildings, the culprit is far more insidious. It's the pipes themselves. Decades of mineral deposits, limescale, calcium, rust, can build up on the inside of galvanized pipes, slowly closing them off like hardening arteries. A 2-inch supply pipe might only have a ½ inch of actual usable space left inside. There's simply no way to get enough water through it to satisfy the demands of a modern commercial flushometer. Another common scenario is the unplanned renovation. A business expands, they build out a new wing, add another bathroom with 3 more toilets, but they tap into the existing, undersized water lines. The original plumbing was never designed to handle that kind of load. Every time a toilet is flushed, it's a battle for water, and the flushometer, which needs a sudden high-volume gulp, is always the first to lose that battle. So before you curse the name of the valve's manufacturer, before you tear apart a perfectly good flushometer for the 3rd time, take a step back. Look at the whole system. Check the control stop. Watch the water flow in the sink. Think about the age of the building and the health of the pipes. Because the hissing sound coming from that toilet might not be the sound of a broken valve. It might be the sound of your entire plumbing system crying out for help. And if you ignore it, it will continue to misbehave, because it's physically incapable of doing the one job it was designed to do. But what if the pressure is fine? What if the volume is a torrent? What if you've checked everything upstream and it's all perfect, yet the valve still won't shut off? Well, that's when we have to look at a cause that is so counterintuitive it fools even seasoned professionals. It has to do with a force that is actually too powerful for the valve to handle. A problem of excess, not of lack. This force is water pressure. Specifically water pressure that is way, way too high. And this is where things get tricky because our intuition tells us that strong pressure is a good thing. We want a powerful shower, we want the sink to fill up fast. But inside the delicate, precision-engineered world of a flushometer, excessive pressure isn't a feature. It's a catastrophic failure waiting to happen. It turns a controlled hydraulic event into a violent, uncontrollable mess. To understand why, you have to appreciate the beautiful simplicity of how these valves are designed to work. The magic happens because of something called a pressure differential. Imagine the diaphragm, that black rubber disc, is like a sealed door between 2 rooms. The room below is the water supply pipe coming from the wall. The room above is the top chamber of the flush valve, right under the metal cap. For the toilet to be off, for that door to stay closed, the pressure in the top room has to be equal to the pressure in the bottom room. The water from the supply line fills both areas, and the downward force on the diaphragm keeps it firmly seated, sealing off the flow to the toilet bowl. It's a perfect, stable equilibrium. When you push the handle, you're not manually lifting that door. You're a saboteur. You're briefly opening a tiny escape hatch in the top room, called the relief valve. This lets the water in that top chamber escape down into the toilet bowl. For a split second, the pressure in the top room plummets. Now the pressure in the bottom room, the full force of the building's water supply, is much stronger. It easily shoves the diaphragm door upwards and whoosh. Water thunders into the toilet bowl. The flush begins. But here's the crucial part for it to shut off. As water is rushing into the bowl, a tiny trickle is also being diverted back up into the top chamber through a small hole called the bypass orifice. Slowly, that top chamber begins to refill with water. As it fills, the pressure builds and starts to push the diaphragm door back down. Once the pressure on top equals the pressure on the bottom, the door slams shut, the flow stops, and the system is back in its stable, ready state. It's an elegant, self-regulating hydraulic dance. Now let's inject chaos into this dance. Let's crank the water pressure from a normal 60 psi to a blistering 120 psi. The system is still in equilibrium when the toilet is off. But the moment you push that handle, all hell breaks loose. You've opened the escape hatch, the pressure on top drops, and that 120 psi from below doesn't just lift the diaphragm. It detonates it upwards with incredible violence. It's not a controlled opening. It's a hydraulic explosion. And in that chaos, the tiny, delicate relief valve, the little escape hatch that you opened, can't close properly. The sheer velocity of the water jetting through the bypass orifice to refill the top chamber is so extreme that it physically holds the relief valve open. Think of it like trying to close a door while a fire hose is blasting it from the other side. You can't. The force is too great. And as long as that relief valve is held open, the top chamber can never fully pressurize. And if the top chamber can't pressurize, the diaphragm can never be forced back down to shut off the water. The result? The toilet runs and runs and runs endlessly. The very force that is supposed to power the system is now tearing it apart from the inside, preventing it from ever completing its cycle. The signs of this problem are often mistaken for something else. You won't just hear a running toilet. You'll hear a very loud, violent flush, often followed by a loud bang or shudder in the pipes as the valve tries to close but can't. This is called water hammer, and it's the sound of your plumbing screaming for help. You might also notice that faucets in the building splash uncontrollably when you turn them on full blast. Your shower might feel like it's sandblasting your skin. These aren't signs of a great plumbing system. They are symptoms of a dangerous system-wide disease. And this is where the story gets much bigger than a single running toilet. A maintenance manager for a small office park I knew was driven crazy by this. One of his buildings had 3 flushometer toilets that would constantly run. He was a smart guy and he did what we've talked about. He replaced the diaphragm kits. They'd work for a week, maybe 2, and then fail again. He replaced the entire flush valves. Same result. He was convinced he was getting defective parts from the manufacturer and spent hours on the phone with suppliers, absolutely losing his mind. He was treating the symptom, the failing valve, without ever diagnosing the disease. The disease was 115 psi of water pressure coming in from the city main. While he was focused on the toilets, that pressure was silently waging war on the entire building. It was putting constant, extreme stress on every single pipe fitting, every angle stop under every sink, the supply lines to the ice maker, and most terrifyingly, the water heater. A water heater is designed to operate around 60 to 80 psi. Subjecting it to nearly double that pressure 24 hours a day is like constantly overinflating a tire. It's not a matter of if it will fail, but when. And for him, that when came on a 3-day holiday weekend. The tank ruptured, flooding the entire first floor, causing over $50,000 in damage, lost business, and a massive insurance headache. The 3 running toilets weren't the problem. They were the warning siren, and he hadn't known how to read the signal. So how do you fight back against this invisible enemy? You start by proving it exists. You need to get a water pressure gauge. You can buy one at any hardware store for about $10. It looks like a little tire gauge and simply screws onto an outdoor hose spigot or the hot and cold water hookups for a washing machine. It's one of the most powerful and underutilized diagnostic tools a property owner can have. Turn on the water and see what it reads. In the United States, standard residential and commercial water pressure should ideally be between 40 and 80 psi. If your gauge is reading 90, 100 or higher, you've found your culprit. And here's a pro tip. Test it late at night. City water pressure often rises at night when overall demand in your neighborhood goes down. You might have 75 psi during the day, but that can creep up to 95 psi at 2 a.m., which is when these failures often begin. Once you've confirmed you have high pressure, the solution is a beautiful piece of plumbing technology called a pressure reducing valve, or PRV. This device is the guardian of your entire building. It's installed on the main water line right after it enters the building, and its only job is to take the high, fluctuating, unpredictable pressure from the city and tame it, stepping it down to a safe, constant pressure that you set. It ensures that every fixture in your building, from your million-dollar commercial equipment to your humble toilet, receives water at a civilized pressure it can actually handle. If you already have a PRV, it might have failed or just need adjustment, which is usually done by loosening a lock nut and turning a screw on the top. But if you don't have one, and you have high pressure, you need to call a plumber and have one installed immediately. It's not just about fixing your toilet. It's about protecting your entire investment from the catastrophic damage that high water pressure inevitably causes. It's the difference between being in control of your building's plumbing and just waiting for the next disaster. So we've tamed the beast of high pressure. The water flows with perfect, civilized force. You install a brand new diaphragm, you set the pressure, you flush the toilet, and it works. Once, twice, then a week later it's running again. The brand new part has failed already. What could possibly destroy a new component that quickly? It's not a problem of force or a problem with the part itself. It's a problem of contamination. A silent saboteur lurking in your water lines, grinding your plumbing to a halt, one grain at a time. This sediment, this grit, is the mortal enemy of the modern flushometer. Think of the inside of your flush valve, specifically the diaphragm assembly, as a high-performance engine. It's a marvel of hydraulic engineering, designed to operate with precision, using water pressure to open and close with perfect timing. The rubber diaphragm seal that presses down to stop the water flow needs to create a surface-to-surface connection as flawless as two panes of glass. Now imagine throwing a handful of sand into that engine. What happens? Catastrophic failure. That's exactly what's happening inside your toilet. This contamination comes from a few usual suspects. It could be sediment from old, corroding city water mains that get stirred up anytime there's a pressure change or a fire hydrant is used down the street. It could be from construction nearby, where new pipes being tied into the system shake loose decades of settled rust and minerals. Or the problem could be coming from inside your own building. If you have older galvanized steel pipes, they are constantly shedding tiny flakes of rust and scale into your water stream. Every time that water flows, it's carrying these microscopic assassins directly towards the most delicate parts of your plumbing system, your flush valves. Here's the core of the problem. The reason a single grain of sand can defeat a $100 piece of precision-molded brass and rubber. When the flush cycle finishes, the diaphragm is pushed down by water pressure from the top chamber, seating itself against the valve body to shut off the water flow to the bowl. For this to work, it needs to create a perfect hermetic seal. But if one tiny, almost invisible grain of sand or a flake of rust gets swept in with the water and lodges itself right on that sealing edge, the diaphragm can no longer seat properly. It's like trying to close a door with a rock stuck in the jamb. No matter how hard you push, the door will never be fully closed. That microscopic gap, held open by a single piece of grit, is all it takes. Water begins to seep, to trickle, past the seal and down into the toilet bowl. It's not a full flush, but a constant, maddening run. You might not even see it, but you can hear it. That faint hiss, the sound of your water bill climbing second by second. And here's the most frustrating part. It can be intermittent. A subsequent flush might have enough force to dislodge the piece of debris, and the toilet will work perfectly. Then, 10 flushes later, another piece gets stuck and the problem is back. This maddening inconsistency leads people to believe the valve itself is faulty, when in reality, it's just a victim of a contaminated water supply. So, how do you diagnose this silent saboteur? The biggest clue is timing. Did this problem start happening right after the city shut the water off for maintenance? Did you have another plumber in the building fixing a different major leak? These events are notorious for stirring up sediment that was lying dormant in the pipes. If your toilet problem started immediately after an event like that, contamination is almost certainly your culprit. The second method is a physical inspection. You have to play detective. Shut off the water at the stop valve, the little screw or handle on the pipe leading to the toilet. Relieve the pressure by pushing the flush handle. Then, carefully unscrew the top cover of the flushometer. Lift out the diaphragm assembly. Now look closely. Do you see any black or brown specks inside the brass body of the valve? More importantly, run your finger lightly along the bottom edge of the rubber diaphragm and the brass seat it presses against. Do you feel any grit? It might feel like fine grit sandpaper. If you feel anything other than a perfectly smooth surface, you've found your problem. Now this is where most people and even some plumbers make a critical mistake. They see the grit, they see the worn diaphragm and they say, "Aha, bad part." They go to the supply house, buy a brand new $5, $10 or $20 diaphragm kit, install it and pat themselves on the back. The toilet works perfectly. For a day. Or a week. Then the running starts again. Why? Because they only treated the symptom, not the disease. They put a brand new pristine part right back into a contaminated system. The very next flush sends a fresh wave of grit and sand to lodge under the new seal, and the whole vicious cycle begins again. You are literally throwing your money away. The real solution, the permanent fix, requires one extra crucial step. Before you even think about putting that new part in, you have to flush the line. With the top of the flushometer still off and the internal parts removed, grab a bucket or a large cup. Hold it over the open valve body and slowly, carefully crack open the stop valve. Water will shoot up out of the valve body. Let it run for 20 to 30 seconds into the bucket. The first blast of water will likely be brown and disgusting. You will literally see the sediment, the rust, the junk that has been causing your problem getting flushed out into your bucket. You are clearing the pipe of all the ammunition that's been aimed at your toilet. Once the water runs perfectly clear, shut off the stop valve. Now, and only now, is it safe to install your new diaphragm kit. By performing this simple flush, you've ensured that your new part is being installed into a clean environment, giving it the best possible chance to seat properly and last for years, not days. For buildings with chronic sediment problems, especially those with old pipes, you might need to take it a step further. Plumbers have a secret weapon for this: an inline strainer. It's a small fitting that can be installed on the water pipe right before the flushometer's stop valve. It contains a fine mesh screen designed to catch all this debris before it can ever reach the delicate internal workings of the valve. It's like putting a bodyguard in front of your toilet. It's an extra cost up front, but it can save you hundreds, if not thousands, of dollars in replacement parts, labor, and wasted water over the life of the building. I remember a project at a brand new multi-million-dollar medical facility. One entire wing of restrooms had toilets that would not stop running. The maintenance crew was at their wits' end. They had replaced the Sloan diaphragms in a dozen toilets 3 times in 2 months. They were blaming the parts, blaming the installation plumber, threatening to rip everything out. I came in and the first thing I asked was, "Did you flush the lines before you installed the fixtures?" Blank stares. We shut the water down, pulled one valve apart, and held a white towel over it as we cracked the stop valve. In seconds, the towel was covered in tiny little copper shavings and solder balls left over from construction. The lines had never been flushed. We spent the next 2 hours flushing every single supply line in that wing. They installed one more set of diaphragms after that, and they never had to touch them again. The problem wasn't the world-class parts. It was microscopic construction debris. So we've covered a faulty part, we've covered incorrect water pressure, and now we've covered contamination from debris in your water line. These 3 account for the vast majority of running toilet issues. But what if you've checked all of that? What if your parts are new, your pressure is perfect, and your lines are flushed and clean, but the toilet still runs? Now we have to look at a much more insidious problem. A problem that isn't about a physical object like a grain of sand getting in the way. It's a problem of chemistry. There's a bizarre chemical reaction that can happen inside your pipes, creating a crystal-like growth that slowly suffocates your plumbing. It fools even experienced plumbers because it doesn't look like a failure. It looks like a rock. And this slow-growing menace is our number 2 reason your commercial toilet just won't stop flushing. But what if the problem isn't a physical object you can see or touch? What if the enemy isn't a broken part or a mineral deposit, but an invisible force? A silent, relentless pressure that is waging war on your entire plumbing system. And the running toilet is just the first white flag of surrender. This brings us to the number 1 reason your commercial toilet will not stop flushing: water pressure. And it's not what you think. It's not just high pressure. It's not just low pressure. It is the unstable, untamed, and undiagnosed beast of dynamic water pressure that is, right now, costing facilities in America billions of dollars. To understand this, let me tell you about a facility manager named Frank. Frank was in charge of a brand new 20-story glass and steel skyscraper, a monument of modern architecture. He had the best of everything: the most efficient HVAC system, the smartest lighting, and of course the most water-conscious high-end commercial toilets money could buy. For the first year, everything was perfect. Then the calls started. A toilet on the 15th floor was running, then one on the 8th, then 3 on the 12th floor. They were all doing the same thing. A slow, constant, almost imperceptible trickle of water from the rim down into the bowl. It was maddening. Frank's maintenance team went to work. They did what anyone would do. They replaced the diaphragm kits in the flushometers. It would work for a week. Then the running would start again. Frustrated, they replaced the entire flushometer valve. A few $100s a pop. That worked for a month. Then, like a ghost, the phantom flushing would return. The manufacturer of the toilets sent a representative. He tested the valves, scratched his head, and blamed the installation. The plumbing contractor who installed them came back, checked his work, and blamed the manufacturer for selling a defective product. Meanwhile, Frank was caught in the middle of this circular firing squad. His water bills were creeping up, first by a few $100s, then a few thousand. He was paying his own staff to chase these phantom leaks, paying the plumber to come back, and buying expensive replacement parts that were failing almost immediately. He was spending a fortune treating the symptom, while the disease was silently killing his building from the inside out. The breakthrough came from a seasoned, semi-retired plumber named Al, who Frank called in as a last resort. Al didn't even look at a toilet for the first hour he was there. He walked right past the pristine, failing bathrooms and went straight to the basement, to the mechanical room where the main water line entered the building. He pulled out a specialized pressure gauge, one with a dial and a red needle that would mark the highest pressure reading it recorded. He screwed it onto a spigot, set the red needle to 0 and told Frank, "Call me in 24 hours. The next day, Frank went down to the basement. The gauge's main needle was reading 75 psi. Perfectly normal, right in the sweet spot for a commercial building. But the little red needle, the tattletale needle, was pegged. It was slammed all the way to the end of the dial at 160 psi. Frank was confused. Al explained it over the phone. "Frank," he said, "your building's pressure is fine during the day when everyone is using water. That's the dynamic or flowing pressure. But at night, when the whole building goes to sleep and all the faucets close, the municipal pressure from the street has nowhere to go. Builds and builds. That's your static pressure. And your system is getting hit with 160 pounds of force every single night. That's not pressure. That's a battering ram." Here is the fundamental truth that is so often missed. A commercial flushometer is a masterpiece of hydraulic engineering. It's not a dumb valve. It's a precision instrument designed to operate flawlessly within a specific pressure window, typically between 25 and 80 psi. Inside that valve, you have a flexible rubber diaphragm. That diaphragm is the brain of the operation. It uses a delicate balance of pressure on the top and bottom to control the flush. It's designed to withstand the force of, say, an 80-pound sledgehammer. But Frank's building was hitting it with a 160-pound sledgehammer, over and over every single night. Imagine trying to write a beautiful signature with a pen, but someone is violently shaking your arm. That's what's happening inside the flushometer. The immense pressure forces its way past the bypass orifice, the tiny pinhole we talked about earlier. It warps the diaphragm, preventing it from seating properly. It compresses seals and gaskets, creating microscopic channels for water to leak through. The valve is trying to close, it wants to close, but the sheer force of the water is physically holding it open. The toilet runs not because the valve is broken, but because it's being brutally overpowered. This is why Frank's new parts were failing. His team would install a fresh diaphragm in the afternoon, when the building's pressure was a nice, stable 75 psi. Everything worked perfectly. They'd test it, sign off on the work order and go home. Then at 2 a.m. the pressure would creep up. 100 psi, 120, 150, and that brand new diaphragm, designed for a long and happy life at 80 psi, would be stretched, stressed, and damaged beyond repair in its very first night on the job. The problem is almost always the building's pressure-reducing valve, or PRV. This is the guardian of your plumbing system. It's a heavy, bell-shaped valve installed where the water main enters your building, and its only job is to take the high, unpredictable pressure from the city and tame it into a safe, consistent pressure for your building. But these PRVs fail. They get clogged with sediment, their internal springs weaken, and they get stuck open. Or sometimes they're just set incorrectly from the very beginning. When a PRV fails, the consequences are catastrophic, and they go far beyond a running toilet. That extreme pressure doesn't just attack the flushometers. It attacks everything. It causes the supply lines for your faucets to burst, flooding offices. It hammers the solenoids in your ice machines and dishwashers until they fail. It puts immense stress on your water heater, drastically shortening its life and creating a serious safety hazard. It's the reason you hear that violent bang in the walls. That's water hammer, a hydraulic shockwave that high pressure turns from a nuisance into a destructive force, shaking pipe fittings loose inside your walls. So the number one reason your toilet won't stop flushing is, in fact, a systemic building failure masquerading as a simple plumbing problem. It is the most insidious, most expensive, and most misdiagnosed issue in all of commercial plumbing. It's the reason why you can replace every part in a toilet, and even the toilet itself, and still not fix the problem. You're not fixing the source. You're just endlessly and expensively patching the damage it leaves in its wake. It's a war of attrition you can never win, because the enemy is an invisible, relentless force that never sleeps. And the most insidious part of this enemy is that it often doesn't live where you think it does. You've been fighting a battle inside the porcelain fortress of the toilet itself, but the real enemy, the true saboteur, might be hiding in the walls, quietly feeding poison into the system. This brings us to our next major culprit, A silent assassin that most people never ever suspect. A failing stop valve and a contaminated supply line. Think about the angle stop. That's the little football-shaped valve coming out of the wall, the one with the small handle that you use to turn the water off to that specific toilet. We see it, but we don't see it. It's plumbing infrastructure, part of the background. In a commercial setting, that valve might sit untouched for 5, 10, even 20 years. It has one job: to stay open and let water pass through. And for 20 years, it does its job flawlessly. But inside that valve, time is taking its toll. Water, especially hard water, is full of minerals: calcium, magnesium, iron, sediment. Over decades, these minerals build up inside the valve body, creating a fine, gritty layer of scale. The rubber washers and seals inside the valve become brittle and hard. It's like plaque building up in an artery. Everything seems fine on the outside, but the inside is a ticking time bomb. Then one day something happens. Maybe the building's water is shut off for a major repair, and the sudden rush of water and air pressure when it's turned back on dislodges a few microscopic flakes of rust and scale. Or maybe you, the diligent maintenance person, decide to finally replace a worn-out flushometer diaphragm. You walk up to that 20-year-old angle stop and you turn the handle. You hear a slight crunch. The valve, disturbed from its long slumber, protests. In that single moment of turning the handle, you've unknowingly released the enemy. A tiny piece of that brittle rubber washer, no bigger than a grain of pepper, breaks off. A few flakes of hardened calcium scale are scraped from the inside of the valve and are sent rushing up the supply line. Where do they go? They go directly into the brand new, perfectly clean, precision-engineered flushometer you just installed. They are injected straight into its heart. And this is where the magic of a flushometer becomes its greatest weakness. For a flushometer to work, it relies on a perfect balance of water pressure between an upper and a lower chamber, separated by the rubber diaphragm. The key to this entire operation is a minuscule hole in the diaphragm called the bypass orifice, or the weep hole. It is quite literally the size of a pinprick. After a flush, water slowly weeps through this tiny hole from the lower chamber to the upper chamber. Once the pressure in the upper chamber equals the pressure in the lower chamber, it pushes the diaphragm down, seals the valve, and stops the flow of water. It's an elegant, simple, and brilliant piece of engineering. But what happens when that single grain of pepper, that tiny flake of calcium from the old stop valve, gets lodged in that pinprick-sized hole? The answer is catastrophic failure. With the weep hole blocked, water can no longer pass into the upper chamber to equalize the pressure. The lower chamber pressure remains dominant, holding the valve wide open. The flushometer is now physically incapable of shutting off. It will run and run and run, dumping thousands of gallons of water down the drain, until someone manually shuts off that stop valve. Now here's the truly maddening part. You see the toilet running. You assume the brand new diaphragm you just installed must be faulty. You take it apart, you pull out the diaphragm, and in doing so you dislodge that tiny piece of debris. You might not even see it. You put in another new diaphragm kit. You turn the water back on. It works. The toilet flushes and stops perfectly. You think you've solved it. But you haven't. You haven't solved anything. Because the source of the problem, the crumbling interior of that old stop valve, is still there. It's a little volcano, waiting to spew more valve-killing grit into your system with the next pressure fluctuation or the next time you turn the handle. So a week later or a month later, the same toilet is running again. You're now convinced you're going crazy. You're blaming the manufacturer of the flushometer. You're blaming the city's water supply. You're blaming everything except the one component you've been ignoring the whole time. This is why, for professional plumbers, one of the first diagnostic questions for a chronically running toilet isn't about the toilet itself, but about the building. How old is the plumbing? When were these stop valves last replaced? A seasoned pro knows that you can install a $100 gold-plated flushometer, but if it's being fed by a $5 20-year-old stop valve that's falling apart on the inside, you are just throwing good money after bad. So how do you diagnose this invisible enemy? It's easier than you think. First, if you have a recurring problem with the same fixture, and new parts only seem to be a temporary fix, this should be your number one suspect. Second, perform a simple test. Turn off the stop valve. Disconnect the supply line from the base of the flushometer. Get a bucket, aim the supply line into it, and crack the stop valve open for just a second. A quick short burst. Now look in the bucket. Is the water perfectly clear? Or do you see tiny black specks, little sandy particles, or a reddish-brown tint? If you see anything other than crystal clear water, you've found your culprit. You are literally looking at the shrapnel that is killing your flush valves. The solution, then, is not to keep replacing the diaphragm. The solution is to go after the source. You must replace the stop valve. This is a more involved job. It often requires shutting off the water to a whole section of the building, not just the single fixture. It requires a pipe wrench and some plumbing know-how, but it is the only permanent fix. By installing a new, clean stop valve, and it's always a good idea to replace the flexible supply line at the same time, you are ensuring that only clean water is entering your flushometer. You are cutting off the enemy supply line, literally. You are ending the war, not just fighting another losing battle. It's an incredible lesson in how complex systems work. The failure point is rarely the big, obvious component. It's almost always the smallest, most overlooked, and least respected part. The entire, powerful, high-pressure operation of a commercial flush toilet can be brought to its knees by a piece of grit smaller than a grain of sand, released from a part that nobody ever thinks to maintain. But what if the stop valve is new? What if the supply lines are clean and the water is pure? What if you've replaced every single moving part inside the flushometer, and yet you can still hear the sound of water running? Sounds impossible. If the valve is closed, the water should stop. But it doesn't. This is because the problem isn't in the valve anymore. It has moved downstream to a place where a perfect seal is being broken by a force you can't see, a problem that masquerades as a flush valve issue but is, in fact, something entirely different. It's a plumbing phantom, and it's one of the most misdiagnosed issues in the entire industry. This phantom is called negative pressure, or more specifically, trap siphonage. And it has nothing to do with the toilet itself, but everything to do with the building's ability to breathe. Imagine a high-rise office building in downtown Chicago. On the 14th floor, there's a men's room with 4 stalls. For 3 months, the facility manager, a guy named Frank, has been waging a losing war against the second stall from the end. Every day, sometimes 2 or 3 times a day, it runs. Not a constant run, but a full phantom flush. Just decides to go all on its own. Frank is a good manager. He's methodical. First, he rebuilt the Sloan flushometer. New diaphragm, new handle kit, the works. The phantom flushing continued. Frustrated, he bought a brand new, top-of-the-line Zurn flush valve and had it professionally installed. 2 days later, his staff reported the ghost was back. He called the plumber back. The plumber, equally baffled, took the valve apart. The diaphragm was perfect. The relief valve was seated correctly. He checked the water pressure to the fixture. It was stable. He shrugged, put it back together, and the next morning Frank heard it himself, the sudden whoosh of a toilet flushing in an empty restroom. This is the classic signature of a venting problem. Every single drain in a commercial building is connected to a vent stack, a series of pipes that run up through the walls and terminate on the roof. These vents have one critical job: to allow air to enter the drainage system. They are the building's lungs. When you flush a toilet, a large volume of water, a slug, drops down the main vertical drain pipe called the soil stack. As this slug of water plummets downwards, it acts like a piston in a cylinder. It pushes air ahead of it, but more importantly, it creates a powerful vacuum behind it. In a properly vented system, air is instantly drawn in from the vent stack on the roof to fill this vacuum, equalizing the pressure. The system breathes in and everything flows smoothly. But what happens if that vent is blocked? Maybe a bird built a nest in it on the roof. Maybe leaves and debris have clogged it. Or in a cold climate, it could be frosted over with ice. Now, when that slug of water from an upstairs toilet comes rushing down the stack, the system can't breathe. It can't draw air from the roof to fill the vacuum. So, the vacuum does what vacuums do. It pulls from the path of least resistance. It will violently suck the air from anywhere it can find it. The first place it looks is the P-traps of nearby fixtures. You'll hear a deep, gurgling sound from a floor drain or a nearby sink. That's the sound of the vacuum literally ripping the water seal right out of the trap, trying to get air. And if that vacuum is strong enough, it will find another path of least resistance: the delicate rubber diaphragm in your flush valve. Remember how that diaphragm works. It's held down by the water pressure in the upper chamber. It's a perfect but not invincible seal. A sudden powerful vacuum in the drain pipe below the toilet can be just strong enough to momentarily lift the edge of that diaphragm, just for a fraction of a second. It's like a little pop. This tiny lift is all it takes to break the pressure seal. A small amount of water escapes from the upper chamber down into the main valve, the pressure differential is lost, and the toilet initiates a full flush cycle. The system has been tricked. The flush valve is performing its job flawlessly, It was just given a false signal by a phantom force from within the building's own plumbing. Back in Chicago, Frank was about to order a third flush valve when he had a moment of clarity. He realized the phantom flushes weren't entirely random. They often happen between 9 o'clock and 9:30 in the morning, and again just after 1 p.m. What happens at those times? The morning rush and the post-lunch rush. He went up to the 15th floor, the floor directly above his problem restroom. It was a busy call center. He realized that at those peak times, multiple toilets were being flushed upstairs almost simultaneously. This created a massive slug of water, a huge piston effect, generating a vacuum his 14th floor plumbing couldn't handle. He wasn't fighting a faulty part, he was fighting physics. He called a different plumbing company, one that specialized in commercial diagnostics. He didn't say, "I have a running toilet." He said, "I think I have a venting issue." The technician didn't even bring a wrench into the restroom. He went straight to the roof. 10 minutes later, he came down with a photo on his phone. A plastic shopping bag had blown onto the roof, been sucked against the opening of the vent stack for the 14th and 15th floors, and formed a nearly perfect airtight seal. He removed the bag, and the phantom flushes on the 14th floor stopped, instantly and permanently. After 3 months of replacing parts, the solution was a piece of trash on the roof. So how do you diagnose this phantom? First, listen. Gurgling sinks and drains are your number one clue. If you flush a toilet and the sink next to it sounds like a monster waking up, you have a venting problem. Second, pay attention to patterns. Does the problem happen during times of high usage in the building? Is it on a lower floor of a multi-story building? Third, consider your own repair history. If you have replaced the internal components of a flush valve, or even the entire valve, and the problem persists, you have to stop looking at the fixture and start looking at the system. The toilet is the victim, not the culprit. The solution isn't about finding a better diaphragm. It's about letting the building breathe. And while sometimes the fix is as simple as pulling a plastic bag off a pipe, it can also involve tracking down improperly installed or even cut and capped vents from a past renovation, which is a serious job for a professional. This system-level failure is one of the most complex and misdiagnosed reasons for a running toilet. It requires you to think beyond the porcelain and the chrome, to see the restroom as part of a larger, interconnected ecosystem. But even this powerful, invisible force isn't the number one reason commercial toilets run. We've talked about worn-out parts. We've talked about tiny debris. We've talked about improper installation and even the building's own plumbing fighting against itself. But we haven't talked about the one thing that every single flush depends on, the very lifeblood of the system. We haven't talked about the water itself. Because the number one cause of a phantom flush isn't a problem with how water leaves the toilet, but a fundamental issue with the water that enters it in the first place. That's right. The number one reason a commercial toilet runs isn't because of a faulty part inside the flushometer itself, but because of the immense, invisible force pushing on it from the outside. We're talking about water pressure. Think of it like the blood pressure of your building. For a human, a healthy blood pressure is around 120/80. Too low and you feel faint. Too high and you're at risk for a heart attack or stroke. A building is no different. Its arteries are the copper and PX pipes running through the walls, and its lifeblood is the water flowing through them. Most commercial plumbing fixtures, from the faucets to the flushometers, are designed to operate in a specific pressure range, typically between 45 and 80 pounds per square inch or PSI. Below that range and you get a weak flush that can't do its job. But above that range, above 80 PSI, you enter the danger zone. And this is where the real ghost in the machine lives. Imagine a freeway where the speed limit is 65 miles per hour. That's your normal 60 PSI. The cars are moving efficiently, they can stop safely, and the system works. Now imagine the speed limit is suddenly 150 miles per hour. That's what it's like when your water pressure is 120 PSI. The water isn't flowing anymore. It's screaming through the pipes. And when a valve, like the one in your flushometer, slams shut after a flush, it's like a multi-car pileup at 150 miles per hour. All of that momentum, all of that kinetic energy has to go somewhere. It can't just disappear. So it converts into a massive, instantaneous pressure spike. A shockwave that reverberates back through the entire plumbing system. This is a phenomenon plumbers call water hammer. And it is as violent as it sounds. You might hear it as a loud bang or a shuddering in the walls when a valve closes. That sound is the sound of your plumbing being physically assaulted from the inside out. This relentless, high-pressure assault is what destroys flushometers. Remember that delicate rubber diaphragm we talked about? The heart of the whole operation? It's designed to hold back 80 psi of pressure. When you subject it to 100, 120, or even higher, you're asking a welterweight boxer to stop a freight train. The high pressure can physically force water past the seal. Even if the diaphragm is brand new, it creates a tiny, almost imperceptible leak into the bowl. The water level in the tank portion of the flushometer drops, the pressure equalizes, and whoosh, a phantom flush. You replace the diaphragm and a week later the problem is back. Because you didn't fix the problem. You only treated a symptom. The real disease, the chronic high blood pressure of the building, is still raging. Over time, this constant abuse takes its toll. The shockwaves from water hammer can fatigue the brass components, cause hairline fractures, and literally vibrate screws and fittings loose. It can deform the precise, molded shape of the rubber gaskets and seals, creating permanent leak paths. That tiny weep hole we discussed? High pressure can force microscopic sediment into it at incredible velocity, blocking it in an instant. The volume regulator ring? It can be vibrated out of its proper setting. Every single one of the other 4 problems we've discussed is made 10 times worse and happens 10 times faster in a high-pressure environment. It is the great accelerator of plumbing destruction. And here's the most insidious part. High water pressure is a silent killer. The running toilet is often just the first, most obvious symptom of a much larger, building-wide problem. If your toilets are running, it's a good bet your faucets are dripping, the solenoids in your ice machines and dishwashers are failing, and the pressure relief valve on your water heater is on the verge of letting go. It's putting a constant strain on every single joint, every valve, and every appliance connected to your water supply. It's a ticking time bomb. The phantom flush isn't just costing you money and wasted water. It's a warning siren telling you that your building's entire circulatory system is under critical stress. So how do you know if you have this invisible enemy lurking in your pipes? You perform a diagnosis. And the good news is, it's incredibly simple. You don't need to be a master plumber. You just need a $10 tool from any hardware store. A water pressure test gauge. It looks like a little pressure dial with a female hose fitting on the back. You find an outside hose bib or a utility sink faucet with a hose connection, you screw the gauge on, and you turn the water on all the way. That's it. The needle will immediately show you the static water pressure for your entire building. If that needle is reading anywhere above 80 psi, you have found your phantom. You've found the root cause. And you should know that municipal water pressure can fluctuate. It's often higher at night when overall demand in the neighborhood is low. So test it in the morning, and then test it again late at night to see the full range. If you see readings of 90, 100, or I've even seen 140 psi in some areas, you need to take immediate action because your plumbing is not designed to handle that kind of force. The solution to this system-wide problem is a device called a pressure-reducing valve, or PRV. This is the master gatekeeper for your building's water supply. It's usually installed right after the main water meter, and its only job is to take that high, unpredictable pressure coming in from the city main and throttle it down to a safe, stable pressure for the rest of the building. Most commercial buildings are required by code to have one. But here's the catch, they fail. Like any mechanical device, they wear out. The diaphragm inside can tear, or the internal passages can get clogged with sediment over the years. Or sometimes they're just set incorrectly by the original installer. A failed or improperly set PRV is like having a security guard who has fallen asleep at his post, letting the barbarian horde of high pressure run wild through your building. Now, adjusting or replacing a PRV is a job for a licensed plumber. This isn't a simple DIY fix. But by taking 10 minutes to test your pressure, you can diagnose the problem with absolute certainty. You can call that plumber and say, "My toilets are running, and I've tested my water pressure. It's at 110 psi. I believe my PRV has failed." In that moment, you've transformed from a victim of a mysterious plumbing problem into an informed, empowered building owner or manager. You've saved yourself hundreds, maybe thousands of dollars in exploratory repairs and repeat visits. You've addressed the root cause, not just the symptom. So let's bring it all home. That phantom flush, that ghost in the machine that has been driving you crazy and draining your bank account, it was never a ghost at all. It was one of 5 logical mechanical failures. Number 5. Debris in the line, the foreign invader causing chaos. Number 4. The wrong volume regulator setting, a simple calibration error. Number 3. A clogged weep hole, a tiny brain aneurysm stopping the flow of information. Number 2. A worn-out diaphragm, the tired heart of the system finally giving up. And the number 1 most common and most destructive cause of them all, Dangerously high water pressure, the silent killer, the chronic high blood pressure of your building that stresses every component to its breaking point. The commercial toilet is not a simple porcelain throne. It's a brilliant, non-electric hydraulic engine that harnesses the power of physics and water pressure to perform a critical task with incredible reliability. But when it fails, it's not out of spite. It's communicating. It's sending you a signal. That constant hiss of running water is a symptom of a deeper problem, a cry for help. By understanding the language it's speaking, the language of diaphragms, weep holes, and pressure, you gain the power to not only fix the problem, but to make your entire building safer, more efficient, and more reliable. You're not just stopping a leak. You're preventing a flood. You're not just saving water. You're saving yourself from a catastrophic failure down the road. What's the most baffling plumbing mystery you've ever had to solve? Let me know in the comments below. I read every single one. And if this deep dive helped you finally understand the ghost in your machine, do me a favor and flush that like button. And be sure to subscribe for more guides to the hidden world of engineering that surrounds us every day. Thanks for watching. Stay curious.